In the last lesson, we learned how to solve equations involving trigonometric functions of theta. Now we're going to be learning how to find the solutions to trigonometric equations where the angle inside of the trigonometric function is not necessarily just x or a. Instead, it might be sine of 2x or sine of 5x or sine of x over 3. And we'd still like to be able to find what the solutions to x are going to be simply by using the same methods that we used previously. Let's start off with this example right here, where we're trying to find out the angles. Keep in mind that this is an angle. And we're trying to find out the angles where sine of x is equal to the square root of 3 over 2. Now I've gone ahead and drawn this piece of the unit circle already. And we should realize that we're referring to where is the y coordinate on the unit circle, square root of 3 over 2. Now in general, we're going to be solving using radian measure, but just for simplicity right now, I've chosen to use degrees. And so we should realize that the solutions to this equation will be x equals 60 degrees, because that's where the y coordinate is root 3 over 2. But also the second quadrant will give me an answer, which is why 120 degrees is my second answer. So this is how we would solve an equation if the angle was simply x. Well, let's say that we wanted to try something different, and we wanted to find out what is sine of 2x. When exactly is sine of 2x equal to the square root of 3 over 2? Now, the first thing you may think is, well, that looks like a double angle, so I could use a double angle formula. But it turns out that using a double angle formula will be more complicated, because even though this is 2 sine x cosine x, we would then deal with two different trigonometric functions. So instead, we'd like to think about what exactly does this mean? And so 2x is now the angle that we're referring to. So what we're really solving here is when is sine of theta equal to the square root of 3 over 2? Well, what we've done already is we recognize that theta is obviously going to be 60 degrees or 120 degrees. But now we've got to realize something important here. Now it's saying that I would have to double some angle in order to get me to the angle of 60 degrees that will give me the answer of root 3 over 2. So doesn't that mean that I would have to take the 30-degree angle, because there are now two of those angles that we refer to as x, in order to get me to the angle of 2x? So in other words, if we take the 30-degree angle here and plug that in, notice that that would give me sine of 2 times 30 degrees, which is now sine of 60 degrees. And sine of 60 degrees gives me root 3 over 2. And we could also look again and recognize that another angle is going to be the angle that's half of 120. Well, half of 120 is obviously 60, and that's because this angle times 2 will give me the 120-degree angle. So in general, when we have an angle that's not exactly just a single variable of, say, x, what we need to do instead is we need to replace that with the angle theta, and now recognize that theta is in fact 2x. And so now we're recognizing that 2x would equal 60 degrees or 120 degrees, which means that half of that, in order to find the value of x, would have to tell me that x is equal to a 30-degree angle, or half of 120, which is also 60 degrees. So in other words, all we had to do was divide the original angles by 2, and that'll tell me what my new angles are. So even though the green angles here were the original, the 60 degrees and 120 degrees, were the solutions to sine of x equals root 3 over 2, Now I realize that when I cut each of these two angles in half, now the angles are going to be 30 degrees and 160 degrees. But that's not actually all, because if we only wanted to find the answers on the interval 0 to 2 pi, turns out that there are actually more answers. Because notice that if we were to take a look at these angles, 60 degrees and 120 degrees wouldn't be the only angles. In fact, we need to recognize that 60 degrees is coterminal to 420 degrees by adding 360. I could see that 120 degrees is coterminal to 480 degrees. Okay, again, by simply adding, I shouldn't say equal, these are different angles. And so notice that there's a couple other angles that are also going to give me the square root of 3 over 2. Now I wouldn't list these because notice that these two angles are beyond 0 to 2 pi, or rather 0 degrees to 360 degrees. So if we wanted the first rotation, that's why we wouldn't list these two angles. However, because we are now going to be cutting a couple of angles in half, we should add a second rotation here of 420 degrees and 480 degrees, because when I now cut those in half, notice that those now give me two more angles that are going to be in the first rotation. The first of which would be 210 degrees, the second of which would be 240 degrees. So we could see where those would be are at 210 down here in the third quadrant, and 240 degrees. So in general, the rule of thumb is if the angle is 2x, we need to write out 2 rotations. If the angle was 3x, we'd have to write out 3 rotations. So notice at this point, the answers to this problem, sine of 2x equals root 3 over 2, are 30 degrees and 60 degrees, both of which, when doubled, will give me an answer of root 3 over 2. And also 210 degrees and 240 degrees, because once those are doubled, I will also get an answer of sine of that value being root 3 over 2. So why don't we do one more by taking a look at maybe sine of 3x. Let's say we had sine of 3x is equal to square root of 3 over 2. But with the same general idea, we need to recognize that theta is the angle that we're solving for. So again, we're writing out that sine of theta is root 3 over 2 when theta is equal to 60 degrees or 120 degrees. Or if I look at a second rotation, I could also add 360 to get 420 degrees or 480 degrees. But because I'm dealing with 3x, that means I need to create a third rotation, which means that now I need another rotation, add another 360 degrees to here, and I get 780 degrees. And if I add a third rotation to here, adding 360, I get 840 degrees. Now notice that all of those angles are definitely not in the interval of 0 to 360. But that's because each of those angles is actually not theta, but in fact, it's equal to 3 times x. So in order to find these angles, we're going to need to recognize that I could cut each of these angles in thirds to find new angles. So if we divide every result by 3, I'm going to only start with the first two in this original first rotation, then notice that I get a couple of answers of x equals 20 degrees and x equals 40 degrees. Which again would mean that I would cut my 60-degree angle right here into thirds. So I would get a 20-degree angle, and I would get a 40-degree angle. And so each of these two angles are apparently going to be solutions to this equation. But again, it should make sense because if I multiply the angle of 20 degrees by 3, I get 60 degrees, which gives me the correct ratio. If I plug in 40 degrees, now and multiply it by 3, I get 120 degrees, which means that at this point, 120, I'm back to the same ratio again. So I already see that 20 degrees and 40 degrees are a couple of answers, but those aren't the only answers, because if I draw a second rotation and divide that by 3, I'm now going to get a couple of other answers, 140 degrees and 160 degrees, which you should realize is basically cutting this quadrant in thirds, which now means that I have 140 degrees is another answer, and 160 degrees is another answer. But finally, by taking my third rotation, when I divide the third rotation by 3, that puts me back into the first rotation again, which is still from 0 to 360 degrees. And so 780 divided by 3 is, what is that? 780 divided by 3 is going to be 260 degrees. And now 840 divided by 3 is 280 degrees, which means that I have this angle right before 270. That's going to be 260 degrees. And I have this angle over here, which is 280 degrees. So it turns out that because of the fact that in one rotation, whenever a trig function is equal to a particular ratio, there are two answers in that first rotation. But once you recognize that you take sine of 2x, that means I'm going to have twice as many solutions. And when I now take a look at 3x, that means I'm going to have 3 times as many solutions. So we're solving this in the exact same way, except for the fact that once we get to the point that we set theta equal to all of these values, we now need to solve for x by applying the operation on that angle. So if we now get rid of these two angles, my only solutions to sine of 3x equals root 3 over 2 will be 20 degrees, 40 degrees, 140 degrees, 160 degrees, and 260 degrees and 280 degrees. All of those will make this equation true. To take it one step further, I'd like to go ahead and focus on these points here, which you could look at on the graph, or you could look at in terms of this list right down here. And we want to come up with the list of all the solutions where we use n to represent all of those particular values. So the first thing to do here is to find out, well, from 20 degrees, from my first, I know that x equals 20 degrees is going to be one of my answers. That's the starting point, or the starting angle. I first of all see if there is a consistent angle from one angle to the next. And I can see that there's not, because this is a small angle, then a large angle, then a small angle, then a large angle. And so I know that there's not going to be any particular one single angle that I can do, or that I can add to get to the next step. So now the next step is maybe we could skip angles. If I skip the 40-degree angle, the distance to here is 120 degrees. So now if I go from 140 and skip the next angle, notice that I add 120 degrees to get to 260. If I now start at 260 and skip the next angle, I land back at 380 degrees, which is 20 degrees past 360. So it looks like I could continue to get to all three of these angles by starting at 20 degrees and adding 120 degrees each time. And so one of my general solutions is 20 degrees plus 120 degrees in. But now I've got to take a look at my other angles, my 40-degree angles, because notice that so far we only have a general solution for 20 degrees, 140 degrees, and 260. We don't have a solution for the other ones. And so notice that we have 40 degrees, and now we're going to see how far it is to get to 160. All right, well, you can see that that's a 120-degree difference. In order to get from 160 to 280, that's the same difference of 120 degrees. And in order to get from 280 plus 120, that takes me to 400 degrees, which sure enough is 40 degrees past 360. So what we see here now is that we're able to find a second general solution that's going to start at 40 degrees, and it's going to take me to every other angle as well. And so notice that if I take 40 degrees and add 120 degrees times n, then those two general solutions will describe every possible answer, no matter how many rotations, to the equation sine of 3x equals the square root of 3 over 2. Now that's one method we could use. We could also use the other method, which is basically just recognizing that in the first rotation, the only answers, okay, the only answers were theta equals 60 degrees or theta equals 120 degrees. Now, there was no way for me to add one particular angle to get from 60 to 120 and then back again to 420. So that's why we just take the first quadrant angle and we add 360 degrees times n. Or we take 120 degrees, the second quadrant answer, and we keep adding full rotations to there. But now, since we were trying to solve for 3x, then what we're going to do at this point is recognize that 3x is equal to 60 degrees plus 360n. And so if we divide by 3, notice that we get x equals 20 degrees plus 120 degrees times n, or 40 degrees plus 120 degrees times n. And so notice that I get the same answers regardless of how I approach that problem. The first way is just a visualization to see how we're actually getting those answers. The second way is more algebraic because I'm just taking the original angles from my original equation. Now let's take a look at a different situation where we've got two different trigonometric functions. So first of all, I have sine of x over 2 is equal to cosine of x over 2. And so since I have sine and cosine, I need to somehow figure out how to change this into one type of trigonometric function. So there's two methods we could do here. One method is to realize that if I divide both sides by cosine of x over 2 and divide by cosine of x over 2, then now notice that the left side of the equation becomes a single function of tangent of x over 2 equals 1. So now we want to determine, where is tangent equal to 1? Well, we know that first of all, these are going to give two quadrants. First of all, it's going to be in quadrant 1 and in quadrant 3. And so we need the first and third quadrant answers where tangent is equal to 1. Secondly, we need to realize that this angle is a half of what we need. So let's start off by calling it theta. And we'll realize that theta is equal to an angle of pi over 4, because that's where tangent of theta is equal to 1. And also the third quadrant pi over 4 angle, which is 5 pi over 4. But keep in mind that that theta is actually x over 2. So what we need to do in order to solve this is realize that x over 2 is equal to pi over 4 and 5 pi over 4. Which means the angle we need must be twice as big. So therefore we get x equals, if I multiply everything by 2 here, I can multiply the left side by 2, and I multiply the right side by 2, and we get our answers of x equals 2 pi over 4, which gives me an answer of pi over 2, and 5 pi over 2, 10 pi over 4, or 5 pi over 2, which is another answer. But if all I wanted to do was find the answers on the intervals 0 to 2 pi, then notice we should be canceling out the answer that's going to take me beyond that full rotation. So really I'm canceling out 5 pi over 2 simply because it's past 2 pi. And so my only solution to this equation is x equals pi over 2. So that's one way to solve this, but it turns out that there is another method of solving this as well, if you didn't notice to divide both sides by cosine. The second method of doing this is to think about an identity that relates sine and cosine. So keep in mind the identity that we should be thinking of is the Pythagorean identity that says that sine squared x plus cosine squared x is equal to 1. But the only way that these two functions, sine and cosine, can be related to each other in this way is if both of them are squared. So since they're on opposite sides, why don't we square both sides, which we're allowed to do through algebra because it maintains the equivalency. And now at this point, we can realize that sine squared of x over 2 can be left as is, but on the right side, we could find that cosine squared of x over 2 is the same as 1 minus sine squared of x over 2. The whole purpose of squaring was so that I could get the same trigonometric function on both sides. So now I've got sine squared of x over 2 on both sides, so if I add the one on the right here to the left, that's now going to give me 2 of those. So that gives me 2 sine squared of x over 2 is equal to 1. And now, like we've done in previous methods, our goal here is just to get sine of x over 2 alone on one side. Because if we could get that trig function alone, we should be able to see a common ratio that we can use. So we can divide by 2. That gives me that sine squared of x over 2 is equal to 1/2. But I'm still not ready until I take the square root of both sides. And when I take the square root of both sides, that's going to give me my result of sine of x over 2 equals plus or minus the square root of 1/2. So if I multiply this by root 2 over root 2 to rationalize the denominator, this gives me the common ratio of root 2 over 2. Now this is by far not the solution because we're still trying to solve for x, but notice how it looks a lot better than what we started with, because not only does it have one trigonometric function, but now we see that sine is equal to the positive or negative of a very common ratio. So if we were to solve this, we should realize that sine is going to be positive in 2 quadrants, but it's also going to be negative in 2 quadrants as well. So I know that sine is going to be positive in quadrant 1 and quadrant 2. But because we also have to find out where sine is the negative of root 2 over 2, we also are going to need a third quadrant point and a fourth quadrant point. Okay, well, we know that sine of x over 2, or sine, if we allow this quantity right here to be theta, then we know that the angles are going to be pi over 4. That's the first quadrant angle. The second quadrant angle would be 3 pi over 4. The third quadrant angle would be 5 pi over 4. And the fourth quadrant angle would be 7 pi over 4. So whenever we take the square root, we can't forget the plus or minus. Okay? But keep in mind that we're actually not solving for where theta equals each of those. We're making sure that we're solving for x over 2. Because now in order to solve for x, we have to multiply both sides by 2 to get our actual solutions. Which means that x is equal to 2 pi over 4, which is pi over 2, 6 pi over 4, which is 3 pi over 2, 5 pi over 2, and finally 7 pi over 2. And so you would think that these are all our answers. But if we look at this other method that we did on the left side, notice that we didn't get all of those answers. We actually only got pi over 2 and 5 pi over 2. We never got 3 pi over 2 and 7 pi over 2. And that's because it turns out that both of these are extraneous solutions. But we would never know that unless we checked them. And so we just have to remember that extraneous solutions can and often do occur whenever we square both sides. If I ever square both sides, then what that implies is that we're going to get answers that could be positive or negative, and therefore we're going to get extra answers. I'm just going to demonstrate, first of all, that if we're only looking at the angles from 0 to 2 pi, we definitely don't need 5 pi over 2 or 7 pi over 2. But I'm also going to show you that plugging in 3 pi over 2 is also not going to work. So every time you square both sides, you do have to do a little bit more work to check for extraneous solutions. So let's just plug that in. We get sine of x, which is 3 pi over 2, over 2. And apparently that's supposed to be equal to cosine of x over 2, which is again 3 pi over 2 over 2. Well, notice that that's telling me sine of 3 pi over 4 is apparently equal to cosine of 3 pi over 4. And if we know from our unit circle that those are in the second quadrant, then we would know that we're absolutely wrong. That would be saying that the square root of 2 over 2 is equal to the negative of the square root of 2, and that's why 3 pi over 2 actually doesn't work. But notice the reason why these extra answers came into play, and that's because if I squared both sides, now the two results would in fact be positive, so they would appear to be the same. So anytime you square both sides of an equation, you always have to check all of your results to make sure that you get something that actually works, which is still why x equals pi over 2 is our only answer. So you do sometimes have options in terms of how you actually solve these equations, but in general, the main point here is get one single trigonometric function, solve it for theta, but then recognize that if theta is anything other than just x, we have to do a little bit more work in order to solve. Now for this last example, I'd like you to realize something very interesting and difficult for this particular scenario. The fact that in one trigonometric function I have 2x, and in the other trigonometric function, I don't have the same angle. So in order to solve trigonometric equations, just like the ones that came previously, every time I saw a trigonometric function, it had the same angle of x over 2. But if I now take a look at this equation, one of the angles is 2x and one of them is x. So I can't solve this until I make both of those angles the same. So this is where, instead of trying to solve this by using the methods we just discussed, instead we would try to change this double angle using a double angle formula. So since I see cosines elsewhere in the problem, I would probably choose to rewrite cosine of 2x using the identity 2 cosine squared x minus 1. Because now, not only do I see the same trigonometric function of cosine, but I also realize that the angles in each trig function are now the same. So once we see an equation where the angles are different, you always need to figure out how can I reduce this double angle or triple angle or whatever it might be to single angles. And so let's go ahead and go through the process of solving. Since we see a quadratic term, we're going to go ahead and subtract cosine x because now it looks like a quadratic trinomial. So why don't we break this up into two separate binomials now? I realize that in order to get 2 cosine squared x, I know one of them is going to be 2 cosine x, while the other one will be cosine x. And if the last term is -1, that means that one of them is going to have to be -1, and one will be +1. So if I now just distribute to check, that's going to give me +2 cosine x minus 1 cosine x, which together gives me positive cosine x. And that's not what I wanted. So notice that must mean that I put the signs in the wrong places. So this should be our plus, and this should be our minus. And so now that we've got two binomials equal to 0, we could just set each one separately to 0 and solve 2 cosine x plus 1 equals 0 and solve for cosine x minus 1 equals 0. So remember, to solve these, you just isolate cosine x, so that means I'd have to subtract 1 and divide by 2. While over on the right side, I'd have to do the same thing, except now I'd have to add 1. And now we should be pretty happy that we see a couple of ratios that are actually from the unit circle. We should realize that cosine is equal to 1 when x is equal to 0. And we can see that cosine x is -1/2. Remember, cosine is negative in quadrant 3. I'm sorry, in quadrant 2 and in quadrant 3. And so my answers that I give should be in quadrants 2 and 3. And so my other answers are where cosine is -1/2, which is going to be at the pi/3 angle in the second quadrant, and the pi/3 angle in the third quadrant. And so all three of these angles are the solutions to x in my first rotation on 0 to 2 pi, which is what I should have stipulated up here as well if we only wanted to find on the interval from 0 to 2 pi. So I'd like to look at what this looks like on our circle when we end up plotting these angles, because we can use that fact in order to find all of the angles from 0 to all solutions, no matter whether it's on the first rotation or the fifth. We can see from our diagram where our solutions are going to be. One is going to be at the angle of 0, one in the second quadrant at 2 pi/3, and one in the third quadrant at 4 pi/3. So if we wanted to come up with a list of all the solutions, then remember that we are assuming that n is some integer. And visually, what we're trying to do is determine if I could add a consistent angle to get from one angle to the next. So from 0 to 2 pi/3 is 2 pi/3 units, or the angle of 2 pi/3 radians. We could see that from 2 pi/3 to 4 pi/3 is also 2 pi/3 radians. And from 4 pi over 3 back to, well, 2 pi is again another 2 pi over 3 radians. So because we were able to get to every single angle by just continuing to add the same exact angle of 2 pi over 3, then I know that the solution for x, when I write it as in terms of all solutions, will be x equals 0 plus 2 pi over 3n. But if 0 is one of my answers, I really could just write it as 2 pi over 3n. So that's how we could look at it graphically, but keep in mind that if you wanted to do this without having to draw it, you could also write these values out in order. And now just determine if you're able to add one consistent angle from one to the next. From 0 to 2 pi over 3 is 2 pi over 3. From 2 pi over 3 to 4 pi over 3 is also 2 pi over 3. But in order to say that this is acceptable, we need to find one more angle that's coterminal to 0, which would be 6 pi over 3, just to make sure that the distance from 4 pi over 3 back to the beginning is also the same. So if we list them in order, we could also see the same result, that we're off by 2 pi over 3 radians. So anytime we deal with solving equations, keep in mind we're solving for angles. But if the angle ever happens to be something other than just x, you either have to apply an identity in order to convert it to a single angle, or go through the process we demonstrated in the prior examples in order to solve for the value of x.